Okay guys, in this video lesson we're going to start our unit on thermodynamics, or basically the physics of heat. Okay, so we're switching gears a little bit from what we have been doing in terms of mechanics, and we're diving into a different kind of world right now. However, this is kind of a transitional unit for us because we're still going to be having a lot of conversations about energy in this unit and the movement of energy. Okay, so to kind of frame what we're going to be doing, we want to think as we go through this whole unit about where is the energy and how is it moving and how is that affecting the objects around it. Okay, that's kind of what we're looking at. So our main topics to study, we're going to deal with this idea of what is temperature versus heat, because they are different things. We're going to get into the second law of thermodynamics, heat transfer, thermal expansion, specific heat capacities, and get into this idea of the first law of thermodynamics, which will lead us into calorimetry. So that's kind of where we're heading. So here we go. The first thing we want to do is take a look at temperature. Okay, now we all know what temperature is, right? We talk about it all the time. Oh, how cold is it outside? How warm is it going to be today? What's the temperature? Usually we work in this weird scale called the I think it's like Fahrenheit or something like that. I'm not really sure. It's just a scale that only a couple countries around the world use. But the most of the world uses this Celsius or Kelvin, so that's what we'll be using in here for sure in terms of temperature. Now, looking at temperature, if we're going to define it in the world of physics, it has a very specific meaning to us, okay? And for us, okay, looking at temperature and relating it back to energy, temperature measures the average kinetic energy of particles in a system, all right? So when we take a temperature, if we go outside and say, hey, today it's going to be 10 degrees Celsius outside, or today it's going to be 0 degrees Celsius outside, which would not be bad, actually. I'd love to have some 0 degrees Celsius around this time of year here in the middle of winter. But a lot of times we get like -5, -10 degrees Celsius here in January, which is kind of cold. Anyway, when we measure that, every single particle of gas out there is not the same temperature. It is not the same amount of energy, I should say, okay? If we average all of the energies that they have, that gives us the temperature, okay? Now, we're going to go to this little applet here, a little distribution applet, I call it. And what it does for us is it shows us that distribution, okay? So if we look on our screen here, we see if this is a random sample of particles. This is probably going to be like a fluid or a gas or something in terms of what we're looking at, because they're able to move around by each other. And looking at this, we see them moving back and forth, but they're not all moving at the same speed. Okay, so some of them are moving faster than others. All right, and what we take a look down here, this is a graph of the different speeds. So the majority of the particles are either this kind of blue, purplish, kind of red color, and they make up the bulk of the speeds of the particles. But we have some way down here that are moving slower, and we have some way up here that are moving much faster. Okay. Now, if we heat this thing up, and we start to heat it up, we notice that we can shift this distribution. Okay. Well, if we shift it, when we measure temperature, temperature measures the average of all of these particle speeds inside of here, okay? So we get a single number based off of the average of all these particle speeds going on here. As we continue to heat, you notice that these are moving much, much faster, because as you warm things up, you make the particles move faster. So higher average kinetic energy, or higher speed, means more temperature, or higher temperature in it, okay? Notice also that this thing spreads out the warmer we get things at. So we actually get a higher range of speeds at higher temperatures. Now I'm going to turn that heater off because we're getting pretty hot. But we still see this distribution of temperatures. Okay, that is why when we look at this idea of temperature, it is not a single kinetic energy. It's the average of all of them. Okay, so keep that in mind, because as we go through the unit, we can't assume that every single particle is moving at the same speed all the time. All we can do is measure that average between those things. Okay. We do need to be aware of the scales that we're going to use, Celsius and Kelvin. Okay, the Celsius scale and the Kelvin scale are the same increments. Okay, so one step up in Kelvin is the same as one step up in Celsius. So if I go from like 0 Celsius to 5 Celsius, it's the same thing as going from 273 Kelvin to 278 Kelvin. It's just 5 ticks up on the scales. Okay, so they're the same scale. They're just shifted by 273. So if we ever have to convert between the two, and we really shouldn't have to in here, but if we had to, it's just Celsius. You have to add 273 to get to Kelvins. Okay, and the reason why the Kelvin scale exists is because Kelvins brings us down to what we call absolute zero. So 0 Kelvins means zero energy, which we'd have zero kinetic energy, so there's zero movement in our system. Whereas 0 Celsius is just a freezing point of water, and 100 degrees Celsius is a boiling point of water. Okay, so that's kind of what we're looking at. This graphic over here just kind of shows more, in a more simple fashion, that distribution of kinetic energies based off your number of particles. So we see it as it's colder, it's a narrow distribution. As it warms up, we get a wider distribution there. Okay, but the take home here is temperature measures average kinetic energy of particles. All right. Now, what is heat then? So if temperature measures the average kinetic energy of particles, heat does not mean hot, okay? Because if we get things hot, that means their average kinetic energy goes up. If we get things cold, that means their average kinetic energy goes down. The word heat actually means energy in our world, okay? So it actually has two definitions, and we can use them kind of interchangeably. The first, when we talk about heat, we're talking about energy flow. So when we heat something, okay, we can get energy to flow between two different systems with two different temperatures, okay? So we can transfer heat, or we can transfer energy between two systems because of a difference in temperature. And we're actually going to study how that works and the math behind it in this unit. The other thing we can look at is heat's also the energy potential of a system, okay? So when you have heat, or you have available energy as potential energy, or we call that sometimes thermal energy, this is energy that we can put to work, all right? So we actually can use this heat energy to do things. We actually can power stuff with it, and it actually is available to do work on stuff, okay? Either one of these definitions work for us, and depending on our scenario or the systems we're talking about, we'll apply them as we move through this unit, okay? Now the take home is, in terms of heat then, what has more heat energy? So a lot of times we look at heat, and it's not the average kinetic energy, it's actually the potential of the energy there, okay? So if we look at these two different scenarios, we have a hot tub that's at 102 degrees Fahrenheit, again, that Fahrenheit scale we talked about. We have a hot tub sitting here. It's definitely hot. And then we have the entire Atlantic Ocean. This is the fin from a whale, by the way, if you're wondering what that is. So if we have the entire Atlantic Ocean and we have a hot tub, we all agree that the hot tub is definitely hotter. It has a higher temperature, okay? However, in terms of heat or available energy to do work, okay, or the available amount of energy that can flow between systems, the Atlantic Ocean has way more energy available, okay? Our oceans are gigantic heat sinks for us. So they absorb heat energy during the day and they release it during the nighttime. That's why when you live next to the coasts or by big bodies of water, like the oceans, you have much milder climates because they're able to thermoregulate the land next to them because they're able to do work in terms of releasing heat energy and absorbing heat energy on the cycles of the sun, okay? In Minnesota, we don't have that because we're landlocked. So, we have the Great Lakes, which cause some other things that go on, but we don't get that effect like people in California and on the East Coast get, okay? So the take home here is having lots of heat does not mean you're hot, okay? Having lots of heat means you have lots of energy available to do things, which may mean you're not very hot, but you just have lots of mass to work with. Whereas if you're very hot, like this hot tub, sure, there's energy there, but not near as much as in the entire Atlantic Ocean in terms of those deals, okay? So as we move forward, think of heat more as energy and think of temperature more as a measure of how hot or cold something is. It's kind of a better way to look at it, okay? That's going to bring us into our laws of thermodynamics, and we're going to end here. Thank you.